you to imagine that you have the graph of y equals x squared on a piece of paper in front of you. Except instead of the entire graph, you only have the segment where x is between 0 and 1. Now imagine what you would see if you were to lift up this piece of paper and hold it in front of your face. And then what would happen if just the graph were to hop off the page and start spinning around the x-axis? To get a better idea of what's going on, let's follow a point on its journey around the x-axis. It makes a circle. And this makes sense because the graph is spinning in a circle around the x-axis. And if we follow another point, it would make a circle as well, although perhaps a different size. Can you visualize what happens if we trace out the path of the entire graph as it spins? I'll let you take a look. Now let's get at the real question. If we cut this graph off when x equals 1 and spin it around the x-axis, it outlines a solid shape. What is the volume of this shape? Meaning, if we filled this in, what would its volume be? Before we answer that, let's formulate an easier question. If we spin a thin bar around the x-axis at the same time that we spin the graph, what shape does that make? And what's the volume of that shape? We see a disc, which looks exactly like a hockey puck since I drew it in black. So how is this related to the entire volume? Well, if we had a bunch of different sized discs, or hockey pucks, we would be able to stack them inside our shape to approximate the volume. And you might realize if we had extremely thin discs, then we would be missing less volume as we stacked them up. Well, that's exactly the right idea. The thinner the discs get, the better they approximate the actual volume of this solid. Let's get into the math behind the idea. We will first find the volume of a single disc. But remember, the discs get crazy thin. So let's call the height dx because it's located along the x-axis, and to indicate how incredibly small it will become. The radius of this disc is simply y, the vertical distance from the x-axis to the graph, but y is equal to x squared. So an equivalent way to write the radius is just x squared. This is ideal because now our variables are all both in terms of x. In case you don't remember, the volume of a disk is pi r squared h. Substituting x squared for the radius and dx for the height, we get an expression for volume of our disk in terms of x only. This is quite powerful. Once you write the volume of one disk in complete generality, meaning only using variables, then you're able to write down a formula for the volumes of all those insanely thin disks with virtually no extra work. Remember, sigma means to add up all of these volumes, and as we fit more and more disks into this solid shape, meaning the number of disks goes to infinity, you see that they must get thinner and thinner. And finally, this gives us the total volume that we're searching for. Hopefully you immediately recognize this as being equivalent to an integral, so we ditch the sigma for the integral sign, keeping our formula for volume underneath, and indicate where we start and stop adding up the volumes of the disks. As practice, evaluate the integral. You'll get pi over 5 cubic units, which is the exact volume of our solid.